Welcome in dark core. 3IATLAS has passed Mars and is now racing toward the Sun, entering a critical stage in its interstellar journey. Early observations have already revealed unusual signs, a strong release of water far from the Sun and a CO2-rich coma, both pointing to a very different composition from typical solar system comets. As it approaches perihelion later this month, astronomers are closely monitoring its behavior under rising solar heat and radiation. In this video, we'll explore the latest discoveries, their scientific significance, and what to expect next. Let's get started. Discovery Update. The story of 3IATLAS began in July 2025 when astronomers using the ATLAS survey in Hawaii detected a faint object moving too fast to be bound by the Sun's gravity. Its hyperbolic orbit confirmed it as the third recorded interstellar object after Oumuamua in 2017 and 2I Borisov in 2019. In early October, the comet crossed Mars' orbital path, and the ExoMars Trace Gas Orbiter captured a distant image. It showed a bright condensed coma but no visible tail, an early hint that this object behaves differently from familiar comets. Spectroscopic measurements from ground-based observatories and the James Webb Space Telescope added crucial data. They revealed that 3IATLAS was already releasing water vapor at around 40 kilograms per second despite being 2.9 astronomical units from the Sun. That level of activity is highly unusual. Most comets don't begin such strong outgassing at that distance. Even more striking was the CO2 to H2O ratio, which is inverted compared to most known comets. Instead of water dominating, CO2 appears to be the primary driver of its activity. Polarimetric measurements supported this picture, showing a scattering pattern consistent with fine-grained or chemically distinct dust. Archival data from the Transiting Exoplanet Survey satellite also indicated early activity around 6 astronomical units, suggesting that its volatile materials began reacting long before it entered the inner solar system. This is rare and implies a composition and thermal history unlike any comet formed near the Sun. All of this evidence points to 3IATLAS as a body shaped in an entirely different stellar environment, colder, chemically distinct, and more volatile than typical solar system comets. Scientific importance and theories. The significance of these findings lies in how they challenge our understanding of cometary behavior. Under normal conditions, water ice doesn't sublimate strongly beyond 3 astronomical units, which is why most comets remain relatively inert until they get closer to the Sun. 3IATLAS breaks this rule. The leading explanation is that highly volatile compounds such as CO2 or CO are buried beneath the surface and began venting at very low temperatures, creating pressure that fractured the outer crust. This allowed both volatiles and water to escape earlier than expected. Another possibility is that its nucleus is unusually porous or fractured, allowing sunlight to penetrate deeper and trigger early activity. Its chemical composition provides a unique glimpse into conditions in other star systems. A CO2-dominated profile implies it formed in the colder outer regions of a protoplanetary disk around another star. This fits with its interstellar trajectory and sets it apart from typical solar system comets that formed closer to the Sun. The polarization signature, the way its dust scatters polarized light, also diverges from common patterns observed in local comets. This suggests differences in dust grain structure, size distribution, or mineral composition. Interstellar dust grains can carry chemical fingerprints of their home systems, so this data may help reconstruct the conditions of its birthplace. Some speculative ideas, like those raised by AVILab, propose that unusual behavior in interstellar objects could point to artificial origins. But in the case of 3IATLAS, the current evidence aligns with a natural explanation: volatile-rich, compositionally distinct material shaped by a distant star's environment. Together with Oumuamua and 2I Borisov, 3IATLAS adds a third crucial data point to a young but growing field: the study of interstellar small bodies. These objects act as messengers from other star systems, revealing how planetary formation plays out across the galaxy. Implications and what's next. The most critical moment in this story is approaching fast. On October 29, 3IATLAS will reach perihelion, its closest distance to the Sun, about 0.53 astronomical units. At that point, it will face maximum solar heating, which will determine what happens next. Astronomers see 3 main scenarios. 1. A surge in activity, solar energy could trigger an intense outburst causing rapid brightening and tail formation. 2. Fragmentation. Like many volatile-rich comets, it may break apart under thermal or rotational stress, revealing its interior. 3. Stable passage. Less likely, but if it remains intact, it could continue its journey outward largely unchanged. The period after perihelion will be crucial for data collection. JUICE, observing from beyond the Sun, is positioned to monitor its post-perihelion evolution because it will be using its slower secondary antenna during this time. Results are expected in early 2026. Meanwhile, telescopes including the James Webb Space Telescope, Hubble Space Telescope, and several ground-based observatories will track changes in its coma and spectrum in near real time. If the comet survives, it will become visible again from Earth in early December, passing at a safe distance of around 270 million kilometers. By comparing its pre- and post-perihelion spectra, scientists can learn how solar heating alters interstellar material, data that no laboratory can replicate. The implications go far beyond one object. 3IATLAS helps scientists refine models of interstellar debris exchange, showing how material from distant star systems can travel across the galaxy and enter ours. Understanding these objects provides clues to how planetary systems form, evolve, and interact over cosmic timescales. This is also an opportunity to improve our ability to detect and study interstellar visitors early. Each new object gives us a clearer sense of how common they are, what they are made of, and how they behave when exposed to our Sun. With improved surveys and early warning systems, future interstellar comets may be studied in even greater detail, perhaps even with dedicated flyby missions. 3IATLAS is unlike any comet we've seen. Its unique chemistry and early activity reveal clues from another star system. What happens at perihelion could reshape how we study interstellar visitors. Thanks for watching Dark Core.